Fucking A. Mhm.
In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of wonder and mystery, sometimes the most unlikely heroes make the biggest impact.
All right, hello and welcome to Ether Cosmology Roundtable number 73. Tonight I'm going to be doing a presentation on inertial forces and where to find them, following a presentation that I did a week ago, or what was it, 2 weeks now, where we covered inertial frames and how they're defined mathematically, how forces are presented in those frames, etc. So now we're going to take a look at what the forces actually are, and then we're going to look at some examples of kinematics and dynamics following the assertions of the last Prezi regarding Newtonian dynamics, specifically in regards to the relationship with mass and force. So we'll see how all that works out when we get into some equations to describe the cosmos. Okay, so a quick recap here. Mass and force equivalence through Newtonian, through classical mechanics, really, we'll call it that. We'll start with the Newton's definition of force, which force equals mass times acceleration, the classic F equals ma. And throughout the Prezi here, you'll see some vector notation, so we'll cover what that means. So when you see something in bold, that's usually a vector, which is a magnitude and a direction. And for the m here, that's a scalar, but we'll cover what that means in the next slide, just to kind of familiarize ourselves with what's being said mathematically, with the least amount of variables to represent it, right? So they have some really cool notations here. So anyway, mass is a constant of proportionality. So in this equation, the mass variable will change and the acceleration variable will change to make the proportional force. And that is what is meant by that, for it being a constant of proportionality. So that is the relationship that is shared with acceleration to define the equivalence of force when you multiply these two together. And then a time derivative of velocity is what predicts inertial forces. So when we talked last week or 2 weeks ago about how they take a time derivative of velocity to look for a change in velocity over time to see if they're in an inertial frame or not. So this is going to be important, that we'll touch back on that as we continue. All right, so vectors and scalars, pretty simple concept here. So Gerardus Bow is going to be our guide here from his book, Geocentricity, Christianity in the Woodshed, where he covers pretty much everything that we're going to go over here. So to define scalars and vectors here. The vector is magnitude and direction. So when you see something in bold, or if it has an arrow hat above it with a direction arrow, that's usually that's indicating that that's a vector. It's a direction and how fast it's moving in that direction. And a scalar is just a magnitude, but it has no vector. So it's just like a value, but it's not going in any particular direction. So that's the relationship that they're using there. So here we're going to look at an example of the forces now as we go through the descriptions of centrifugal, centripetal, Coriolis, and Euler forces. So here we have mass, and we're going to use an example of a mass of a box that we're going to pick up, and we're going to do some stuff with it. So keep that in the back of your head. M is a constant of proportionality. So when you go through the equations to figure out the relationship with the force that's being produced, that will be, that's how that will relate with the equivalence. And scalar, again, just magnitude, no direction. Gravity here is going to be represented by minus g with a bold there. So it's going to be, the minus is notating that it's downward vector. And let's see here. So in the box example, right, if you have a box on the ground and it has some mass, you pick it up, you feel the weight of it, you feel that gravitational acceleration, you feel that force when you're holding the box. That's the relationship that we're looking at there. So now I'm going to read through his examples here of what we're going to do with this box and how it relates to the forces. The forces are going to be covered or color notated. So purple will be centrifugal. As we read through, it'll make sense. You can kind of figure it out here. So yellow is just nothing important. It's just, filler words. And then force is just in blue here. So force is needed to change an object's location or direction of motion. You exert force to lift a box from the floor. As you hold it aloft, you feel the downwards force called weight. Because of the gravitational field that Earth exerts, an acceleration, usually noted as minus g, where the minus indicates the downward direction. If you were holding the box and you spin it around, you would feel a force pulling the box out from your body. This is commonly called the centrifugal force. If we set the box on a rotating platform, such as a carousel, step onto the carousel and pick up the box and walk around, we would feel the force that fights us to deflect from a straight path. That force is called the Coriolis force. And finally, back on solid ground, if the box is contained with a spinning gyroscope, we can manipulate the box in various ways, such as turning it upside down, and that would cause strange reactions to the gyroscope. So that would be the Euler's forces when an external frame is rotating relative to the other frame. The force thus reacts with the motion of the gyroscope in the case called Euler forces. So the centripetal force. So think back to the centrifugal force case experiment. With the inward force you exert to keep the box in as you spun around with the box, you consider that a real force, and that's the centripetal force. So if you're spinning like a string and a ball around, the force that is keeping the ball taut would be the centripetal force, and then the force pulling it outward would be the centrifugal force. I'm sorry, the force keeping it tied to you would be the centripetal force. So that's the relationship that it would share there. So the outward force that you fought to keep the box next to you is due to a fictitious force called the centrifugal effect. So you're going to notice here that they try to say that some effects are, fictitious, but they have an effect. Well, how does a fictitious force have a real effect? So they try to conflate the two, and we'll see why as we continue here. But but to be clear, all these forces are real forces. They're inertial forces. They're real. And as from the geocentric perspective, that's how you would count them as real forces. You wouldn't count them as fictitious or anything like that, like how they try to do here. But we'll continue on. So still, you felt the outward fictitious force, didn't you? So how come you have two types of forces? Real forces, which are known as inertial forces, which are the ones we mentioned earlier, centrifugal, centripetal, Euler, and Coriolis, and their equal and opposite effects, also known as fictitious forces. The difference between real and fictitious forces is an artifact of Newtonian chicanery to populate the Copernican system with proofs. Oh, no way. They're going to do some algebraic flip-flopping, I bet. Where have we seen that before? So that's how they're going to substantiate it. In the theory of geocentricity, there is no distinction between real forces and fictitious forces. Both are real, both are real inertial. That is to say, gravitational forces. So in his conceptualization of it, he's saying for his model, it was like there's a firmament that's going to rotate a gravitational field, like the mass of the firmament is going to produce like a mass distribution that when rotated is going to um, cause inertial forces through a medium. So he was an ether lad. So this is what he was putting forward here. So anyway, go ahead and continue on. But so when he talks about gravitation, like don't get all caught up on that. He's just talking about the force that would be created by the rotation of the universe around the Earth. No matter what coordinate system you believe it's represented by. So further, in the geocentric theory, inertial force is a synonym for gravitational force, specifically the gravitational field, which I call the cosmological or the cosmic gravitational field. So in mainstream astronomy and physics, sometimes you'll hear astronomers and physicists argue between is gravity a force. Some will say that it's a fictitious force, it's a pseudo force because because at the grand scale, Einstein's space-time curvature takes over, and that's what produces gravity, right? It's an effect of the bending and warping, excuse me, of space-time, rather than mass attracting mass or something like that, where it's considered a force in Newtonian dynamics. Whereas in Einstein's thing, it has to be the bending and warping of the universe due to the mass distribution of said universe. So I hope that clarifies that. So here we have Tony Coriolis, the only Coriolis I know of. We're going to get into some instances of where they say that they've measured Coriolis here. So the big thing with before we move on, the big thing with the centripetal and centrifugal forces for how they relate big G for gravitation to explain their cosmological belief system, they're equating that to an equivalence to the centripetal force pulling you in. And when we get into the experimental evidence of that, such as Michelson-Morley, where the Earth would have to have a certain velocity through the cosmos to, for these equations to have physical meaning, no such velocity has ever been represented. So the whole backwards derivation of Cavendish to big G, just measuring it off of little g and off the torque angle and all that, and then backwards, and then using Earth's radius to come up with the density of Earth based off of all that. None of that is physically meaningful at all, but it does give you values that you can use for cosmological constants to, role play and stuff, but it doesn't mean that they're physically meaningful or have any bearing on reality. So we'll go ahead and continue now so we just covered centripetal and centrifugal forces in relation to how they say that the Earth is rotating, but gravity and it's canceling it out and all this stuff. None of that has ever been substantiated on the scale that they've talked about it on. So now we're going to look at Coriolis, and this is Tony Coriolis. Like I said, the only Coriolis that I've ever met or had or encountered. So let's do a brief reading here of the Coriolis effect again. So if you were holding the box when you spin around, you would feel a force pulling you outward from your body. We commonly call that the centrifugal. And then if we set the box on a rotating platform, such as a carousel, step onto the carousel and start walking in a straight line, we would feel a force that fights us to deflect us from that straight path. That is called the Coriolis force. So if we live on a rotating ball, then there's going to be a Coriolis force produced by that. And a Coriolis force is perpendicular to the direction or to the plane of rotation. So what that means is if you were in the northern hemisphere and you were shooting towards the south, there would be a deflection to the west. And if you were shooting from the southern hemisphere to the north, there would be a deflection to the east. So you would have to account for these things. And they tell us in different manuals that they account for these corrections, such as military. There's a couple of military manuals where they say that they mention that. There's a couple where they don't. There's this big back and forth between, do snipers have to account for it, et cetera, et cetera. Well, when you get into range tables for like artillery weapons and stuff, they say that, you have to account for it, just trust us. And it's this little tiny minuscule correction, blah, blah, blah. Like nobody would ever know. Oops, just backed out of that. So we're going to look at a real world practical example of where it would be mandatory to account for Coriolis and see how that played out in a real world example here. Actually, 1 second. Okay, that's going to be upcoming. I apologize. Let's see, present. All right, and then okay, so the Coriolis force, that's going to be your deflection that's fighting you from your straight path there when you're perpendicular to the plane of rotation on a sphere. And then so the Euler force would be the manipulation of an external frame relative to the rotating frame. And I don't know of any force I don't know anyone that's ever claimed that sort of thing. So I don't know how that relates to what they would use for globe proof or anything like that. But this is what that force would be. Now, these forces, are they fictitious or are they real? Well, we already covered an example earlier with Michelson-Morley, how on the cosmological scale, big G isn't accounted for. On the micro scale and the subatomic with quantum, big G isn't a factor, little g isn't a factor. So they don't account for any sort of gravitational forces on that scale. It's only to describe the motion of planetary bodies using them as a constant for a ratio against a periodicity, which gives them the illusion that they're in agreement with giving a physical explanation to why something's moving in the sky. So to recap here, geocentric is a description where the forces are always real. They're never apparent or fake or fictitious or anything like that. Heliocentric brings them into fictitious pseudo forces. They're not real. They induce effects. They say that it's an effect of being, of what reference frame you're in, whether or not the effect is going to be apparent or whatever. So they kind of conflate everything and make it hard to understand there. And then when they get into the math side of it, well, the masses in the equations actually cancels out. So none of what they do is actually really meaningful on the cosmological scale. As we continue here, we'll see that the force was made, or I'm sorry, that the choice between real forces or fictitious forces is going to be made philosophically, because as we go through here, we're going to show mathematically there's no distinction between calling them either. They're both represented by the same thing. So the Earth, is it an inertial frame or non-inertial frame? Well, the laws of physics were derived here, and the laws of dynamics are only satisfied with respect to the lab frame. And the kinetic energy potential converted, the potential energy converted to kinetic will tell you the proper outcome for the conservation laws for momentum and energy. So the lab frame, is looking pretty inertial. That's a good place to start. Only when it comes to measurements of light do we get like in anisotropy and the speed of light do they say that the Earth is a non-inertial frame, because if the Earth were an inertial frame in correspondence with Einstein's postulates, then an observer in the east-west directions would measure the speed of light being the same that it is in the north-south directions. Yet on Earth, the north-south variance appears to be constant relative to what they say is the constant speed. But the east-west directions have a velocity boost and retardation going in the east-west directions. And they explain that by the Earth physically rotating out from underneath the constant speed of light. So the observer is physically moving out from under it. It's in a different location. That's how they're explaining the measurement, because it's so small and slow and you're so tiny on this big Earth, you would never know. But the light it can measure the difference because it's, wavelengths. It's really small, really fine measurement. So that's where they're determining that the Earth is a non-inertial frame. And then, of course, there's the Coriolis claims that they say, which we'll get into, not to even touch on the plane where it doesn't matter where you plot your trajectory or what type of plane you're in. You could fly all around and never have to account for Coriolis forces or make any corrections like that. And we'll get into a world record long distance shot that really solidifies the fact that the Earth does not move out from underneath anything or cause any sort of effect like that would cause like a deflection. And then they have the Earth's oblateness. So remember, they say that due to the spin of the Earth, the centrifugal force, pulling the Earth out is cause the Earth to become oblate. But that's measurements with respect to the stars. No one's ever substantiated that. That's, this is a model that they've put forward that exists through the eccentricity value for a deviation of their perfect amount. Like that doesn't doesn't substantiate anything about their model. So when we get into the long distance shot in Coriolis here, this is what is his name? Shepard Humphreys. Shepard Humphreys, and this man a couple of years ago hit a target from 4.4 miles away, and he shot in the south to southwest direction. And we'll get into why that's important here in a second. Because if the Earth is a rotating ball, then the best way to account for Coriolis force is to shoot to the east. The Earth rotates, they say, west to east, which creates the effect of the sky rotating east to west. So if that were the case, then to make this variable something that you don't have to account for, you would shoot to the east. And that would be the best way to min-max that. And when you get into these long-distance shooter types and the people that he was running with, these are all professional shooters, former military people. They're not out there cracking beers and, shooting willy-nilly for funsies. These are people that are min-maxing to do everything they can to make sure that they hit that shot. They want the best statistical odds to hit that shot. And it would be, if the Coriolis force was a factor that was meaningful, to account for that, to reduce it, you would shoot to the east. That would be direct globe evidence, in my opinion, if he had to do this. Because keep in mind, the time of flight was like 25 seconds. So that's going to be a huge deflection there. And so Jaron actually reached out to this guy when he when he got the record, and he emailed him and asked him about Coriolis corrections and stuff like that. And he emailed Jaron back and said that he didn't make any Coriolis corrections. And to account for Coriolis, based on all the other variables, like the wind primarily, that at that distance would be like having a 500-pound person buy thin inner tubes for their bike so that they could have an advantage in a bicycle race. Like, it's just not gonna be a real thing that they're concerned with or going to be able to account for. So the best way to do that would be doing it to the east. And the fact that they just completely neglected it and shot south to southwest is insane. And I think that this guy knew the significance of this, because I'm going to give you some follow-up here. So when Jaron first emailed him, the guy was like, look, I'm not a flat earther, blah, 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 but here's my inner tube analogy about the bike situation and accounting for Coriolis versus the other variables that are at play. So even at this distance, right? So sub 4 miles, anyone that said, oh yeah, we got to Coriolis it up, this dude, no. If it was a variable that meant anything, they would have to be addressed. But anyway, we'll continue on. So Jaron sent him. So I talked to some Globe lads, and they put forward that the direction that he must have shot in, if he didn't account for Coriolis, is in the eastward direction, because that would be the direction where you would minimize the effect to pretty much nil, and you would be able to, you wouldn't be affected by it, essentially, right? So that was the prediction. So Jaron emailed him and asked him what direction he shot in, and he emailed Jaron back and said, don't tell anyone this, but we shot south to southwest. And before he emailed that to Jaron, I went to their website, the nomadriflemanwebsite.com, which is where they posted, this is the range that they did the record on. And in the record here, you could see the moon setting. So we know which direction the target was when we go to look at it. And I went to mooncalc.com or whatever it is, .net, and west by southwest. So at the time of the shooting too. So that's direct evidence against Coriolis force affecting anything or having any meaningful play. So any instance where anyone has shot something sub 4.4 miles and they said they've accounted for Coriolis, whatever they accounted for wasn't Coriolis. That was not a factor that was at play. So kinematics versus dynamics. Dr. Bennett likes to preface that his old professor used to like to say that if you want your students to remember something, you should repeat it 3 times. So kinematics means measurement and prediction of future motion without regards to forces. Kinematics means measurement and prediction of future motion without regards to forces. Kinematics means measurement without regards to forces and predictions of future motion. Dynamics is predictions of future motion using forces. Dynamics is predictions of future motion using forces. Dynamics is predictions of future motion using forces. Hopefully, everyone remembers those two things, because the big assertion of the correctness of the interpretation of all this math and physics is that there's a difference between kinematics and dynamics, where we're doing physically meaningful equations and representing real actual forces in the frames that the measurement or whatever you're doing the prediction for represents. So when we get into a system of centrifugal versus centripetal forces here, we can consider a rotating system that involves like similar to the spinning box experiment. So if we have Fi for our centripetal and Fe for our centrifugal, we see that they're equal here. And when we do the F times A for them, we see that that's the same, but we can further reduce this down and cancel out the masses on both sides there. And then we're just left with the acceleration. So the mass cancels out and the force depends on the acceleration only. It doesn't have anything to do with the inherent property of mass of matter. So here's a little Sean Connery that he points out in regards to kinematics and dynamics. So the first equation that we're looking at is for the angular momentum, right? How to determine the velocity of something that's rotating based off of the angular rotation rate and the dot product of the radius, or distance to the radius. And that will give you the velocity, the rim velocity, right? And you could rewrite that as m times v to make it momentum, because that's what p represents. So you could have the same equation and make it dynamic. You could introduce dynamics. This first equation is just kinematics. Now we're introducing mass. But what happens here is the mass cancels out on both sides, and we're left to solve this the same way we normally do. But because we have P in here, which is associated with mv, putting the mass in it as a dynamic, no physicist would ever argue against this as being like a dynamic equation, although the mass in it canceled out. It's not a relevant factor in determining it, in determining the angular momentum there. That's pretty interesting how that works. Let's see here. I think I covered everything for that. Okay, so now with that said, with this relationship, Bo's going to do a little celestial kinematics and celestial dynamics. So setting up a situation where a firmament, like a celestial sphere. So here we have the Earth, right? So we have a little tiny ball Earth in his conceptualization. Not going to get into it, but just here we have ball Earth. And here we have the firmament. This big circle here is the celestial sphere, the firmament. And the stars are fixed here to them. And they're going to rotate with the firmament. Now, what's going to keep the star from drifting? Well, he's going to show us the kinematic equations to describe that. So keep in mind, to walk us through here for our variables, F is going to be the net gravitational force exerted by the star onto the Earth. So basically what he's going to show here is he's going to derive acceleration independent of the mass of Earth, and then he's going to use that to describe all the forces based off of that acceleration and how that would influence the Earth with respect to sidereal rotation and the declination of the star relative to the equator, the celestial latitude as measured from the equator. So, okay, so F is going to be the net gravitational force. A is going to be the acceleration of the star experienced about its daily path. R is going to be the shortest distance from the axis of rotation to the star. So this is going to be our axis of rotation for the firmament around us, going east to west. And the distance R here is going to be what that represents. It's not to be confused with like R at the center of a ball, kind of R. So D is going to be the distance from the Earth to the star. So here's going to be this angle with our little baby delta. The delta angle here is going to be that relationship to this is going to be our equatorial relationship to the latitude of to the celestial latitude of the star. V is going to be the velocity of the star, which is going to be derived through from the acceleration here. Then we have the angular omega, which is going to be our rotation rate of the firmament. So that's going to be represented by our sidereal time. So the only variables that are going before that we're going to use when we get started here that we're going to actually input would be sidereal time and the elevation angle, that declination angle. So the hourly angle and all that would be the relevant information that we need to get this going. It's like I said, he's going to independently derive the acceleration without the mass. So he gets into the equations here, and we're looking at some calculus here. We'll break down what this means from equation 4. So the acceleration is defined independently of Earth's mass. So we have the change in time, so like the change in position with respect to time. That's what this is. So there's no mass here, there's no m, there's no anything. We're just doing the change over time of this position with respect to time. And with that, he's going to, it comes out to be an acceleration. So as we further break that down, A is going to be the second derivative of R, which is just that position with respect to time again. And then we could, when you can further break that down to that just being how they would derive velocity, which is the change in R over the change in time. So just how, is this, when this is moving, is it accelerating or is it just a velocity? You can derive all of that from this now. So acceleration is the time derivative of velocity. Acceleration equals a change in time over a change in velocity. So is there a change in velocity over time? Yes or no? That's going to determine if there's an acceleration. That's going to determine what inertial forces are produced by that acceleration. No Earth mass required here. And we're on track now to start describing angular rotation here. So just to reiterate, the rotation depends on how R changes over time, not how massive the Earth is. All right, so to continue on now, we're going to introduce the variables to describe sidereal rotation so we can get our rotation on. And so now we've independently derived acceleration of the mass without using the mass of the Earth. We can modify the formula here with the omega and the cross product of R, which is that distance for the change. So that'll give us the tangential velocity of the from the uniform rotation of the axis, which is the d, which is the change in position over the change in time. And then when we do second derivatives of that, we can figure out the acceleration. And because this is kinematics, you could say that that this d here, that this distance and that this r is changing because the Earth is accelerating, it's moving. Or you could say that it's because the Earth is stationary and this is, rotating around us. That would be the equivalence, because in kinematics, relative motion is true. There's no distinction between you moving away from me or me moving towards you. So anyway, that's what that represents. And then what we have over here is he continues to show, based off of the changes in time, what the forces would be predicted off of that. And so the Euler force here would only be significant if the length of sidereal time changed. So this is pretty much not accounted for here, but he's got it in there. And then we have the Coriolis term, which would be for objects moving or rotating. And then we have the centrifugal, which is always present in uniform rotation. So all these variables here that he's now worked into the equation based off of starting with the deriving acceleration independently of Earth's mass using change in position over time. Okay, using the second derivatives of change in position over time. Okay, so in the final form, after he starts reducing this down, in the final form here, we have the centrifugal forces and the Coriolis forces, which are going to offset the star drift. So that's going to keep it from deviating in the firmament as the Earth, or as the firmament rotates to create sidereal time. That's what's going to mediate the displacement of the stars to keep them fixed. So remember, the only thing we started with in this was just the declination angle and sidereal time to get the angular velocity, which we convert into radians using 2 pi. All right, so let's see. As we continue here, the finalization of the equation breaks down into 2 parts. So we have the unit vector for rotation along the axis. We have the horizontal distance axis to the star. We have the d sine and d cosine for which is going to produce the vertical offset for the centrifugal and Coriolis force that's going to, or sorry, centripetal force that's going to keep the star from, deviating. All right, so that's all derived just kinematically, right? We haven't done any mass stuff yet. Now, but what he can do at the end here, he shows that you can throw in mass in the equation. Oh no, did we just so the beauty of this is, right, we don't know the mass of the stars, but in heliocentrism they do. So we could input any mass value here for this, and because it's just going to cancel out, we still make the correct prediction. So it doesn't matter what the mass is in like how we're relating this to the kinematics of celestial mechanics. Just because there's an M in here now doesn't mean this is any more significantly valuable than it was previously before the M's were added. Same equation, the acceleration is equal to minus the angular or minus sidereal time squared times the change in position, the radius, that distance, or change in position minus the distance times the angular or the unit vector for the angular or for sidereal time times the sine of delta. That's all we started with. Now we just enter in an M right here before this A, and we enter an M next to the W here, or next to the omega. They could be any value. Doesn't matter what it is. They cancel out, and we still make the same prediction. Is this more physically meaningful now? Do we have a stronger stake and claim for celestial mechanics now? Conclusion, as he wrote here, some of the book was like, it's an old copy or whatever, so I had some of it summarized by ChatGPT so that it would look nice on the copy paste. So anyway, he writes, conclusion. We have shown that the physics of the geocentric universe accounts perfectly for what we see and measure for the daily rotation, whether that rotation is the Earth within the universe or the universe around the Earth. In the final analysis, proofs based on dynamic equations are not proof of anything, nor are they proof against a geocentric universe. And well said, because as we went over earlier with Michelson-Morley, the velocity would have to be produced for that. Right? They say that they can measure the rotation of the Earth. They can measure the much smaller physical displacement due to Earth rotation, but they can't measure a displacement due to the Earth physically being in a different location in three-dimensional space, because it has a 30 kilometer a second velocity. It's the great bamboozlement. So these equations, although they have dynamics in them, although they're supposed to be representative of dynamics, sometimes it's just a ratio of a constant against a periodicity, and that shares a proportionality that allows it to have symmetry and look like you're giving it physical meaningfulness, right? But it's not. And in some cases where the mass cancels out, it's not a factor. It's about it's always about the acceleration. Nobody knows what the cause is. Right? Some people will say ether, some people will say electromagnetism, electrostatics, et cetera, et cetera. Some people say it's mass itself because of the relationship in F equals ma. So the mass is the force that's attracting, right? That's a Cavendish. But that's not the correct interpretation, and none of these equations that are used have led to experiments that physically verify, what would be needed if they were physically valid to represent an actual force or timing difference due to Earth changing in position over time. All right, so that's it. That is the presentation. Does anyone have any questions, comments, or anything like that?
Dude, that's great. That really gave me a better background understanding for the argument for the geocentric satellites, right? When you put forth that the actual forces, real or otherwise, involved in keeping so-called satellites in so-called orbit revolve around stationary Earth and centrifugal, Coriolis, and Euler forces specifically.
Yep.
So that's excellent. Excellent to give that the proper contextual background.
Yeah. Thank you, man. Yeah, Bowden, or sorry, Bow. I keep wanting to go back to Malcolm Bowden, but yeah, Bo laid it out pretty pretty nicely here for us. And then he gave his own little derivation where he was like, you guys wanna play? I know. I can do some math. I can do some math. I can do a little calculus for you. You guys want to do some cross products? Oh, so yeah, that's kinematics and dynamics, man. That's how they get us every time. And again, this is where they've taken dynamics to the cosmological, because these equations make the correct predictions on the ground and with things that we could measure and experience, but cosmologically they've never been substantiated. And that is the big distinction that needs to be made, is that just because you have a variable in there that is said to represent dynamics doesn't even necessarily mean that it represents dynamics in the way that you think it does.
Right. The way I think about it now is that kinematic, meaning like little g is basically kinematics, observable, empirical. You got measurements. It's a measurement. It doesn't really tell you the cause, why it's falling down, just that it is falling down the rate at which it does so. And then you have dynamics being their derivation of big G, or so-called derivation of the gravitational constant, which would be the actual dynamic force putting that thing in motion and causing it to fall down to the ground at that rate using mass and acceleration, right? So that's like, I think, a good breakdown. But they've combined those two things. Like if you ask the average glober, they're like, little g comes from big G, and it's like, show me 2ht like over t squared. Like, what do you mean? Where's big G coming from height and time? And I'm dropping an object to kinematically measure just just speaking of it. So like, I think that's my new inner breakdown when I start thinking about these things. Like if I have to explain it to someone, what do you think?
Show me where the big G exists.
Or, yeah,
it's like, well, I mean, that's the cause of the little G. Yeah, I know, but like, how? Show me, show me specifically. And they're like, well, I mean,
some guy said that. Like some guy had some perfectly good, valid laws called Kepler, right? He had already put down the ellipticity of the orbital bodies down to the semi-major axis, came up with his rules to describe the motion was solid and rock solid. And then Newton came along and took all the same stuff and was like, behold, the algebraic trick, and now it's mass. Actually, everything that you have is now mine, and it's because of mass attracting mass. Like literal voodoo. That's how I think the historical record should have happened.
Yeah, I mean, that's pretty much what happened. They just kind of, the boys got
years,
so the boys got together and kind of decided to tell this story, and it was like working out mathematically, and they just kind of kept convincing themselves. Like, I don't know if it happened or started out as like, like, oh, coincidence, it just happens to work out, and it was kind of innocent, and then it developed into like, we can never let it go. We have the ring, right? Like, dude, they become Gollum, dude.
Newton put forth the thing, made the claim, I am king, right? I invented calculus, also masters the dynamic cause of everything because I said so, behold. And then for the next 200 years, they were like trying to prove it. They were like, well, it must be because he said it. So how would we prove that it is? And no one's ever done it, right? They've been trying to do it ever since. Leads you to the intro for Michelson-Morley, and then, everyone knows the rest, so to speak. So since that declaration, they've been trying to, justify that declaration, I would say. And I don't think it's ever been done, because that leads up to, the gravitational constant, the Cavendish, the so-called torsion balance, inferring a density based on sun angles to get a radius, the calculated actual density of Earth using physics constants. So that's what started it, right? The whole Keplerian Newton dilemma.
The Keplerian jihad, they call it.
The Newton jihad, I don't think. Keplerian was going strong.
The Dune reference, the Butlerian jihad, very similar. Anyway, yeah, but I appreciate
Sean Connery film, Alan. Do you have a favorite Sean Connery film?
Highlander.
That's a good one. Mine's League of Extraordinary Gentlemen.
Ooh, you beat me to it. That was gonna be mine too.
That's yours too.
Have all the time in the world.
He does lean into his own accent hard there, doesn't he? That's an interesting thing to see.
Yeah, there was something I wanted to show you. Okay, yeah, so check this out. Newton's original definition of force was stated as a change in momentum, not to be confused with the mass relationship, like proportionality thing. But we will not go that far here. Instead, we shall write Newton's definition of force of F minus ma equals 0, which today is rewritten as F equals ma. So the rewriting of the summation of forces equaling 0 to describe the acceleration has been rewritten in a way that presents it that like this relationship of mass and acceleration, causal mechanism, proportionality type thing.
Yeah.
So isn't that isn't that cool how they just like reinterpreted it so that they could like whatever the story was, they just were like, we need more now.
Well, all right, dude. You remember we were talking to that dude, and I think it was in Geo's, and we were talking about the story, and his like recollection of it was so contextually different than ours. He was like, "Isn't it so lucky that Newton knew the centrifugal force formula well ahead of time and knew that it would actually equate, with loosely the gravitational force, and then when plugged it into Kepler's, knew that the mass would equal out, proving his own deduction." And we were like, "Wow, we remember that very differently." Where the whole thing got tricked and you did some algebra and mass was inserted as the dynamic cause because of the relationship of centrifugal and gravitational forces, because that is, of course, when the mass cancels out, right? When you set centrifugal to gravitational force in the calculation of an orbit of around a bigger body. So, I mean,
unlucky.
Yeah, we see it one way, and suddenly they teach it very differently. Like, look how genius these guys were when they worked together to create this dynamic kinematic amalgamation. And we're like, what?
Yeah, they certainly did a number on us through the presentation. And then like, I like my new favorite way of looking at it now is like, because they've got Einstein in such a way where it's like, if they ever had to abandon it, they could always go back to like sweet baby Newton.
Yeah, it's a step.
If they ever had to, like, they could sweep baby Newton back into it because they've already built such lore and established everything off of that interpretation that like it would be like physics would look completely different.
Yeah,
if they tried to like have a different model. It's actually kind of crazy how everything worked out.
The way that they have it today, like if you research Kepler's third law from Newton, right, they'd be like, oh, isn't that a nice, elegant example of exactly how we proved the kinematic and dynamic relationship between the forces that move the celestial bodies? It's like, what? That's not the right context at all. It's almost directly the opposite of that. But if you look it up, you don't know anything, that's what you come away with, right? They're like, oh yeah, sure, that trick you showed me was neat, but it just proves my thing, not your thing.
Just my thing, dude. That's the thing. It's like they want mutual exclusivity over math, and it's like you guys want to go through a bunch of algebraic shuffles where what you're asserting cancels out, and then you're still gonna look me in the ocular and tell me that it's the cause.
Okay. Yeah, they do, dude. I've tried it. Right, just go through like force, weight, density, buoyancy, and mass, and just every time it mentions little g, swap that bad boy out with a little a. Replace that little a with like 2 h over t. I think I forget the formula, but whatever the kinematic derivation for height and time is, and then boom, all those formulas are different, and they're meaningful for us. We can derive little g as an acceleration on the fly, no relation to big G at all, right? And they like lose their minds over that.
Yeah, this is a battle of trying to maintain mutual exclusivity over the cause of the acceleration.
Yep.
So nobody knows. Don't get gaslit. That's all. You don't have, if someone like, you don't have to have an answer because like literally nobody knows. The greatest physicist of the time. No one knows. It's between it's between using tensor calculus and assuming the mass and energy distribution of the universe to describe space-time curvature, or whatever.
Which is gay. Yeah.
Like there's a limited amount of options of where they could go. And they've reached, we're looking at the end of it. All right, lads, if there's no further questions or comments or anything like that, we will wrap up the Prezi. Thanks everyone for attending. Hope everyone enjoyed. And we will be back. What's tonight, Shane? Tonight's Tuesday. What do we got coming up on Wednesday, sir? Or actually, before we get into what we have coming up in the week, what do we have coming up later tonight, brother? I heard you have a podcast you're going to be a part of tonight.
Yeah, we're going to be going to chill on Strange World with Mark Sargent and our friend Lisabeth. Right?
Nice, dude. Tell Lisabeth said what's up.
An hour from now.
Yeah, it'll be super late for me, but yeah.
Nice.
Now, yeah. So people should go hang out there and check that out.
Nice.
And then we got TikTok coming up,
probably stream it in here.
We will definitely be watch partying it here on Aether Cause. So if you're not on the Discord already, you're probably like, socially awkward, but that's okay. You can rectify that by clicking the link in the chat and joining the Discord. And then you can come and watch the thing with us where we watch Shane talk about the globe or whatever, or flat earth or whatever you're talking about when you go on there.
Who knows?
Could be anything at this point. So now that we've covered the itinerary for tonight, Wednesday, TikTok raids with the boys, little celestial theodolite battling.
Gonna away game celestial theodolite as a weapon.
Take it out for a drive.
Weaponize.
Ready for the Globers to straw man the argument over and over? I'm down.
Gonna drive by weaponize.
Absolutely.
Alan, why do you hate refraction? Alan, why don't you account for refraction?
Wait, do you guys believe in refraction or not?
Yes.
So bad.
Oh yeah. So stay tuned. I'm going to upload later a conversation. Oh, thank you, Lily. Speaking of the Brushtail Babe, do we have a coffee ad, Lily, before we continue on with what we're doing throughout the week?
Oh, sure. Yeah. Well, you can finish and I'll do mine last.
Okay, cool. All right. So Thursday, we may do a home game on TikTok, depending on how the raid goes. If we'll see what happens there. And then Friday will be a community event, whether it be Flat Earth Fridays or an Aether Cosmology Twitter space, or we'll join a community space or something. We will do something on Friday. And then Thursday will be Glowbusters. Make sure everyone tune into Glowbusters on Sunday, where I will be giving a further iteration of this presentation, a little more refined view. Going to add a couple of things for the prez on Glowbusters, make it a little longer, break things down a little more clearly. And so stay tuned for that. That's the schedule for the week.